So now that we've talked about power series and how to determine the radius and interval of convergence for a power series, I want to play around with a particular power series in the hopes of creating what we call a power series representation for a function. Now, I want to look at this power series. Pretty simple one, right? N equals 0 to infinity, x to the n. Okay. So when n is 0, I get 1. When n is 1, I get x to the first power, and x squared, x cubed, and so on. Right? So this is the series. But if you look at this series here, this is a geometric series where the ratio r is the variable x. Notice if I multiply 1 by x, I get x. X times x is x squared. X times x squared is x cubed. So this is a geometric series with a equal 1 and r equal to x. And we know from geometric series that it's going to be convergent for what values of x? Since r is x, it's when the absolute value of r is less than 1, so when the absolute value of x is less than 1. In other words, x is between -1 and 1. And in that case, we also know the sum. So we haven't talked about sums of any of the power series yet, just where they converge. But this one we actually know the sum. Remember what it was? A over 1 minus r. A is 1, r is x. This is the sum for any value of x. Now we have what we call a power series representation of this function, f of x equals 1 divided by 1 minus x. But it's only valid on the interval from -1 to 1. So the function 1 divided by 1 minus x is equal to this power series for all values of x between -1 and 1. Isn't that just awesome? Right? So now, instead of just simply taking a function where I can plug in, let's say I plug in, I don't know, 0.2, right? What's f of 0.2? Well, I do 1 minus 0.2 is 1 divided by 0.8. I can simplify that down and evaluate the output to the function. Instead, now I can do what? I can take that 0.2, right, and plug it in for x here. 1 plus 0.2 plus 0.2 squared plus 0.2 cubed plus 0.2 to the fourth, and so on. All I need to do is just do that an infinite number of times, and I'll get the same answer. You say, what? What kind of craziness is that? Why would you want to change a simple function that we can plug in to some, difficult thing to try and compute? Okay, well, certainly for this function we might say that. But the thing is, we can create other functions like this where the power series is very helpful. And if we want to evaluate the functions, and sometimes they can be difficult to work with, we can use the power series or even a truncation of it. In other words, we can sort of estimate by stopping after, say, the first 5, 6, 7 terms or whatever, depending on how rapidly the series converges. In other words, how rapidly these terms diminish to 0. Because eventually these terms down here, if it's convergent, they're going to get really, really small. I mean, just so insignificant that, as far as rounding off goes, we don't even consider them as having any effect. So you can sometimes represent more complicated functions as a truncated version of a power series. And there's some other things that we're going to do with it in terms of differentiation and integration as well. And from this, we'll also be able to generate power series for functions, the antiderivatives, namely of functions that before we did not have a way to express their antiderivatives. Okay, so I'm kind of getting ahead of myself. Let me just play around with this particular power series and show you how one way we can create new power series representations. We're going to do this for these functions, and we're going to give the corresponding interval convergence. And I'm going to do this function first and just sort of see how we can play around with this. I'm going to replace, if you compare this function to the function here, all I need to do is what? Replace x with what? 2x. So I'm simply going to replace x with 2x. So 1 divided by 1 minus 2x, the function is, and I'm going to replace x with 2x, so I've got 2x to the n. Now what is 2x to the n? That's 2 to the n, x to the n. Right, so there's the power series representation. I can actually write out the first few terms of this, right? When n is 0, I get 2 to the 0 is 1, x to the 0 is 1. When n is 1, I get 2x When n is 2, I get 2 squared is 4x squared. When n is 3, I get 2 cubed is 8x cubed. N is 4, I get 16x to the 4th, and so on. There's my power series representation. Now, what's the interval of convergence? Remember, it used to be x between -1 and 1, but we replaced x with 2x. So now 2x is between -1 and 1, and if I divide all three values by 2, I get -1/2 less than x less than 1. So there's the interval of convergence. New power series representation for this function. Okay. So let's try this again. This was pretty simple. Just replace x with 2x. So we're basing everything off of this one, right, that we know. Try to build new ones. So here's one. How in the world do I get this one? I'll give you a little hint. It was 1 over 1 minus x. How does this get to be like that? 1 over 1 minus something. What goes in there? If you said negative x squared, get yourself a cookie. That's good, right? Negative x squared, right? That's going to give us that. And so I'm going to replace x with negative x squared. Okay? And so this function, 1 divided by 1 plus x squared, is equal to, remember the function before was what? X to the n, but we're replacing x with negative x squared to the n, right? And this is what? -1 to the n times x to the 2n. Right, if I distribute that exponent of n. And so let's look at some terms in the sequence. When n is 0, I get 1. When n is 1, I get -1 to the first power is -1, so I'll just write it as minus x to what? 2 times 1, x squared. Then when n is 2, I get -1 squared is +1, 2 times 2, x to the 4th. And then you see what happens. It's an alternating series, right? Plus minus, with only even powers. So there we go. There's our power series representation for 1 divided by 1 plus x squared. And what's the interval of convergence? Remember, x was between -1 and 1. X was between -1 and 1. We replaced x with negative x squared. Okay. Now, first of all, I'll multiply everything through by -1, and when I do that, I get 1. Notice when I multiply by negative quantity, what happens to our inequality? Changes direction. Okay. So -1 is just, or x squared is now between -1 and 1. Another way of saying this is simply to say that x squared in absolute value is less than 1. And if you look at that, think about that, just think about the graph of x squared. We know what that graph looks like. So what's the absolute value of x squared look like? The same thing. This is indeed the absolute value of x squared, right? It's because x squared is always non-negative. And we were saying what has to be less than 1. So here's y equal 1. Well, right there, right, it is 1 squared, right, will give me 1. And what's back here? -1 squared. So basically, any values of x between these two numbers, right? So what's our interval of convergence? It's x is between -1 and 1 again. So we have a new power series representation for the function 1 divided by 1 plus x squared. Okay, let's do one more. And again, we're going to use this power series that we started with up here. This time I want you to look at this. And here I'm going to help you out a little bit too. Function 1 over x. You say 1 over x doesn't look anything like that. How do you get that to look like that? Well, note the following. Right? If I do 1 minus the quantity 1 minus x, distribute that 1, I get -1 plus x. 1 minus 1 is 0. I just get plus x down there. And so what are we going to do? We're going to replace x with what? 1 minus x. There we go. And so 1 over x is equal to n equals 0 to infinity. Replace x with 1 minus x. Write out some terms of this series that we're adding up. When n is 0, I get 1. When n is 1, I get 1 minus x. When n is 2, I get 1 minus x squared, 1 minus x cubed, quantity cubed, and so on. And what is our interval of convergence? Remember, it was x between -1 and 1. We replaced x with 1 minus 1. Sorry, 1 minus 1, 1 minus x. Right. And then to get x by itself, I'm going to subtract 1 from all sides. And then to get this to be x, I multiply everything by -1. 2 changes the direction when I multiply by -1. 0 times -1 is still 0. This is one way of writing it. Another way is just to rewrite it as what? In that order, right? And so this is my interval convergence. My interval convergence. So for any real number x between 0 and 2, I have a power series representation for 1 over x right here. Now again, you're thinking, if I want to evaluate the function 1 over x, I can plug any value of x other than 0 into this thing and get the answer quick, right? Why do I need this thing again? So again, just illustrating how we can manipulate power series to create power series representations for other functions, and there are some very useful ones. This one's actually a pretty important one. Another way we can build power series functions is by term differentiation and integration. And I think we'll look at that in the next video.